seemingly unsinkable ore carrier Edmund Fitzgerald disappears into the dark waters of Lake Superior. Investigators search for the cause of two deadly Boeing 737 crashes. In 1959, a nuclear disaster near Los Angeles is hidden from the public. An oil tank collapse unleashes almost 4 million gallons of oil. And microscopic gremlins knock out everything from satellites to personal computers. Now, engineering disasters on Modern Marvels. On November 10th, 1975, the 29 crew members of the 729-foot ore carrier, Edmund Fitzgerald, were fighting an intense storm on Lake Superior. Their destination that day was the protected area of Whitefish Bay on Michigan's Upper Peninsula.
We're at Whitefish Point, just in front of the light station. Today the winds are only about 20 miles an hour. Can you imagine what it would have been like with 96-mile-an-hour winds? These waves are only about 4 or 5 feet today, but they were 35 feet back in 1975.
When the storm had passed, the Edmund Fitzgerald was to deliver its iron ore to its final destination in Detroit steel mills, where the ore would be used to make cars. Despite the storm, the men were confident in their safety because the Fitzgerald was one of the strongest and most capable ships on the lakes.
This was a big, powerful boat, and people really wanted to be on the Edmund Fitzgerald. This was the one you aspired to serve on.
In fact, when it was launched in 1958, it was the premier ore carrier on the Great Lakes, setting records for the largest loads carried and the fastest trips. The captain, Ernest McSorley, was also one of the most experienced in the business, with 44 years of sailing on the Great Lakes. But on November 10th, 1975, McSorley was virtually blinded by two critical navigation system failures. He reported to a nearby ship that both of his radar units weren't working, and the radio direction finder was useless because of an outage at a station on shore. That nearby ship, a few miles behind, was the Arthur Anderson, a slightly larger carrier also trying to reach Whitefish Bay. Captain Bernie Cooper, using the Anderson's radar, was radioing general compass headings to the Fitzgerald's crew. The pilot house of a ship nearly identical to the Fitzgerald, the William Clay Ford, at the Dawson Great Lakes Museum in Detroit, gives a sense of what the captain and crew of the Fitzgerald were dealing with on November 10th.
This is the radar unit on the William Clay Ford. It's very similar to the one that was on the Edmund Fitzgerald. The Edmund Fitzgerald's radar unit, however, that night was out. For whatever reason, both units didn't work.
Why both of the Fitzgerald's radar units didn't work remains a mystery. There were no reports of problems before the ship left port. It's possible that the huge waves or high winds disabled the antennas on the Fitzgerald's roof. But the Anderson battled the same storm without any radar problems.
The other option they had was to use the radio direction finder. With this, they could triangulate their course. However, the Whitefish Point sending station was out of service.
On shore, the radio direction beacon at the Whitefish Point lighthouse didn't work. The storm had knocked out power, and the backup generator didn't kick in as it was supposed to. These failures may have doomed the Edmund Fitzgerald. At about 3:30 in the afternoon, McSorley reported to Cooper that one of the fence rails, part of the sturdy safety fences on each side of the Fitzgerald, had snapped. He also said two vent covers were missing, and the ship was listing to the side, evidence that water was entering the Fitzgerald. These were all signs of severe damage, but the ship soldiered on, pumping out water as it went. Then at 7:10 p.m., the first mate aboard the Arthur Anderson asked McSorley how the men of the Fitzgerald were doing.
The response back from Fitzgerald to the Arthur Anderson is, "We are holding our own." That was the last communication between the two ships.
Minutes later, the Edmund Fitzgerald disappeared from the radar screen aboard the Arthur Anderson, without as much as a distress signal. After a difficult and limited search during the storm, and a larger search the next day, it was clear the unthinkable had happened.
It looks from the information that we have that it's fairly certain that the Fitzgerald went down, and we're talking now about a matter of life and death and looking for survivors.
The massive Edmund Fitzgerald and her crew of 29 men were gone.
We can only ask the masters to do.
6 months later, the cameras of a remotely operated U.S. Navy submersible spotted the wreckage, agonizingly close to safety, just 17 miles from Whitefish Point. Those first images of the wreck, and footage from many other dives over the years, showed that the ship lay in two pieces on the bottom of Lake Superior, with its back, or stern, resting upside down. The ore pellets from the cargo hold were strewn about, and the middle 200 feet of the ship had disintegrated into small pieces. But finding the wreck didn't provide answers to the questions about what caused the Fitzgerald to sink, and why the crew never called for help. More than 3 decades later, strong opinions still surround the theories of the ship's tragic fate. A Coast Guard investigative board looked into many possibilities. Probably the only one that they could confidently rule out once the wreck was discovered was the possibility that the Fitzgerald had broken in half on the surface.
The ship didn't break in half because the bow would have floated for a while longer and the stern would have floated for a while, and they both would have disappeared a little bit further apart.
Instead, the two pieces of the ship lay only a few hundred feet apart. In terms of official findings, the Coast Guard report issued on July 26, 1977, concluded that water crashing on the deck and leaking through cracked and poorly sealed hatch covers was the most likely cause of the disaster. The seals on freighter hatch covers were often damaged during loading and unloading, and crews often skimped on the tedious process of tightening most of the hatch cover clamps. Still, many people disagreed with the Coast Guard's theory.
If water was leaking in through the hatch covers, then the pumps that were on, these 7,000 gallon per minute pumps, and there was 2 of them going, should have been able to keep up with as much water that these hatch covers would allow through leaking.
The Lake Carriers Association, which represented 15 shipping companies, protested to the National Transportation Safety Board, which issued its own findings on May 4, 1978. The NTSB also focused on the cargo hatches, but in a different way. It felt the tremendous weight of the water crashing across the Fitzgerald's main deck, known as the spar deck, forced one or more of the hatches to implode and swiftly flood the cargo hold.
You can tell by the size of these things, the 729-foot freighter, these things weigh tons, and it would take an awful lot of weight to cause them to implode.
Finally, the Lake Carriers Association proposed its own theory, that the Fitzgerald struck bottom in the shallow waters around Caribou Island, a plausible consequence of the ship's navigation system failures. Hitting bottom could have caused a rupture in the hull below the waterline. The downed fence rail and missing vents the McSorley reported near Caribou Island seemed to bolster that scenario.
This was serious. How serious? Not serious enough that McSorley thought he couldn't continue on. He had his pumps going. He thought he had it under control. But as Bernie Cooper pointed out later, it's serious when a fence rail comes down. That indicates an incredible change in tension in the hull itself.
The type of tension that would result from the middle of the 729-foot ship hitting bottom.
And if you hog a ship, meaning cause it to bend up in the middle, you can stretch those cables and cause them to snap because they're supported with stanchions all the way along. Something's got to give.
But since there are no scrape marks on the portion of the hull wreckage that can be seen, bottoming out, like the other explanations, remains just a theory. However, one thing most of these theories agree on is that the Fitzgerald was taking on water faster than it could be pumped out. And the more water that came in, the lower the ship would ride in those high seas.
The waves were actually boarding the Fitzgerald on the starboard quarter, rolling the full length of the deck, the spar deck, and hitting the back of the pilot house and actually forcing this 40-foot high structure underwater, and it'd come back up and shake the water off the deck and keep going. But one of those dives that did under one of these huge waves was the final dive, and it just kept going 535 feet to the bottom.
If McSorley believed the ship would resurface after that final wave, then the first sign of trouble, and the last, would have been a wall of water bursting through the windows of the pilot house from the increased pressure of deeper waters. This would explain why there had been no distress call. But there's still no single theory about the tragic fate of the Edmund Fitzgerald that will satisfy everyone. The bodies of all 29 crewmen remain entombed in that watery grave, and at the request of their families, divers are no longer permitted near the wreck. But those relatives do have two special places where they can feel close to their loved ones. Just outside the Dawson Great Lakes Museum in Detroit, an anchor that belonged to the Edmund Fitzgerald prior to its last voyage is displayed.
It is the centerpiece in the annual November memorial. We put 29 lamps out here around it, one for every crew member on the Edmund Fitzgerald.
And at the Great Lakes Shipwreck Museum at Whitefish Point, the original bell from the Edmund Fitzgerald is the centerpiece of the collection. Known as the voice of the ship, it was recovered from the wreckage at the request of the families on July 4th, 1995.
When this bell broke the surface after 20 years of darkness and silence, it actually swung and tolled, and everybody around for about a mile could hear it. It was one of the most eerie experiences I've ever had, and the tone itself has such a resonating quality to it that is something that you'll never forget.
After the original bell was recovered from the wreckage of the Edmund Fitzgerald, a replica bell was put in its place. The names of all 29 crew members were inscribed on the replica, which serves as a permanent grave marker. Engineering Disasters will return on Modern Marvels. We now return to Engineering Disasters on Modern Marvels. About 1 million people worldwide fly in a Boeing 737 every day. During its decades of service, the plane has compiled an impressive safety record. In fact, the 737 quickly became the workhorse of the commercial airline industry after its debut in 1968. But a fatal flaw caused at least 2 crashes and led to the longest investigation in the history of the National Transportation Safety Board. In 1991, United Flight 585 crashed into a park in Colorado Springs. The pilot had been making a routine landing approach at 1,000 feet when the plane suddenly banked to the right, turned upside down, and plummeted nose first into the ground. All 25 people on board were killed. The investigation proved to be especially difficult.
The flight data recorder was an older type that only had 5 parameters, so we didn't get a lot of data from this. The aircraft itself was severely damaged and disintegrated by the impact. Many of the components were difficult to test.
After nearly 2 years, the frustrated NTSB investigators were unable to determine a definitive cause. 2 probable theories surfaced.
It may have been a mountain rotor from winds coming off the mountain, sort of a horizontal tornado, or possibly a failure of the aircraft's rudder control system. But there wasn't enough information to decide either way.
Then, in 1994, an eerily similar second 737 crash occurred. This time, U.S. Air Flight 427 approached Pittsburgh on a calm September evening. It passed through some turbulence from the wake of a plane a few miles ahead, which momentarily surprised the crew. It should have been easy for the experienced pilot to make a simple adjustment. But the 737 suddenly banked hard to the left, turned over, and spiraled into the ground. All 132 people on board died. Investigators rushed to the scene, immediately aware of the similarities to the 1991 Colorado Springs crash. This time, they had more information to work with.
We had more flight data recorder parameters. And also, with US Air 427, the rudder power control unit that controls the rudder was intact. It was in a testable condition, which we didn't have before.
The rudder of an airplane functions much like the rudder of a ship, turning the aircraft to its right or left, which is known as yaw. Flaps on the wings, known as ailerons, control the roll of the plane to the left or right. Adjusting the horizontal stabilizer on the tail affects the pitch, which raises or lowers the nose of the plane. But extreme rudder movements can affect more than just the yaw of an aircraft.
What happens when the rudder reaches its full travel limit is that the airplane slips through the air sideways. And as a result, for airplanes that have swept-back wings, one wing develops more lift than in the other, and the airplane then starts to roll.
At relatively low speeds, such as during takeoff, or in the case of both crashes, on approach to landing, if the extreme rudder position is not corrected, the rudder will overpower any aileron adjustments and force the aircraft all the way over, leading to a nosedive into the ground. But initial tests of the US Air rudder equipment didn't reveal any defects. Because the US Air crash happened on a clear evening with little wind, adverse weather could be ruled out. The only other possibility seemed to be pilot error or disorientation. To test the motion effects recorded from the US Air flight in 1994, investigators went to the NASA Ames Research Center in Northern California, home of the world's largest flight simulator. Unlike other simulators that simply pivot on a stationary platform, the center's vertical motion simulator can move 60 feet up or down and 40 feet side to side.
Pilots that we've had from all over the world that have come in to fly the vertical motion simulators say that it replicates flight like no other simulator they've ever been in.
Technicians loaded information directly from US Air 427's flight data recorder into the simulator's computers.
Operate.
The result, seen here using the same US Air flight information, was a chilling reconstruction of what the crew most likely saw and felt.
As we roll out, there'll be a wake vortex upset that resulted from a 727 that was flying ahead of the 737, and that started the maneuver. Right there you feel the wake vortex upset. The pilot then tries to right the airplane, but during that process the rudder then goes over hard to the left, and so as a result the airplane rolls uncontrollably to the left and must have been terrifying in the cockpit.
Nothing from the work in the vertical motion simulator led investigators and motion experts to believe that pilot error or disorientation were factors in the crash. They returned to the rudder control system, but could still find no sign of malfunction. Then, a vital clue. In June 1996, an East Wind Airlines pilot reported rudder problems. It seemed like the hydraulic system of his 737 was actually pushing back when he depressed the foot pedal that controlled the plane's rudder. Luckily, the plane didn't crash because the incident didn't occur during takeoff or landing. This incident led NTSB investigators to examine how the rudder could have moved opposite of the pilot's control. They focused on the hydraulic heart of the system, the rudder's dual servo valve power control unit.
It's about the size of a soda can, and within inside of that is a valve about the size of a pencil that's got ridges in it, and it moves back and forth and ports fluid. That's the primary valve. Around that is a slightly larger valve, cylindrical in shape with ports in it, and that's the secondary valve.
When a rudder is operating normally, only the inner primary valve is supposed to move. Depending on which direction a pilot wants to turn, The hydraulic pressure either extends or retracts a piston, which then turns the rudder. Once the pilot's foot is off the pedal, the pressure is released, and the rudder returns to a neutral position. The outer secondary valve only moves if the smaller primary valve becomes stuck. Virtually all aircraft systems have both a primary and a backup, an important design feature known as redundancy in the airline business. But since the 737's rudder power control unit used two valves within the same hydraulic system, the valves were not totally independent of each other. In 1998, investigators discovered how the valves had created the deadly problem.
We saw that if the secondary valve were to be jammed just slightly off neutral, and you put in a high rate command into the primary valve, you could misport the fluid, hydraulic fluid, and cause the rudder to reverse operation. This would be very similar to driving your car. You turn to the right, the car goes left. You probably will keep trying to turn to the right. You won't figure that out before you go off the road.
The longest NTSB aircraft investigation in history was finally over. 4.5 years after the U.S. Air 737 crash in Pittsburgh. Instructors immediately taught 737 pilots ways to correct the problem, such as momentarily removing a foot from the pedal to release pressure in the event of a jam, and switching from the primary to the secondary hydraulic master control for the entire aircraft in order to free the rudder. The training continues today because the new units with two completely separate rudder control systems are still being installed. In fact, the retrofit process won't be complete until near the end of the decade. However, the planes are still safe in the meantime, thanks to extensive pilot training. And the 737 seems destined to remain the workhorse of the industry as the design changes are completed. Since the 737 debuted in 1968, Boeing has built over 5,000 of the planes. That makes the 737 history's best-selling passenger airplane. Engineering disasters will return on Modern Marvels. We now return to engineering disasters on Modern Marvels. In 1959, just 30 miles from downtown Los Angeles, a little-known nuclear disaster began to unfold at an important Cold War facility. The Santa Susana Field Laboratory, created by the government's Atomic Energy Commission and operated by Rocketdyne, played a vital defense role by producing powerful rockets. 2,800-acre site was built in the hills above Simi Valley, a town of 8,000 just west of Los Angeles's San Fernando Valley. Besides rockets, it was home to several experimental nuclear reactors, which the Atomic Energy Commission hoped could be commercially viable. One of them used sodium instead of water as a coolant. It was known as the Sodium Reactor Experiment, or SRE. But the experiment would soon trigger a technological nightmare.
This reactor was built in an era of nuclear cowboys. The Atomic Energy Commission came out of the Manhattan Project. There was a culture of secrecy. There was a sense of excitement about pushing the limit on these reactors.
On July 26, 1959, technicians barely managed to manually shut down the sodium reactor when temperature and radiation readings quickly jumped. Then, after 2 hours of basic inspections, they made a baffling decision.
They started up the reactor anyway. They operated the reactor for about 2 more weeks before the radiation levels, and there were so many signs of trouble that thought it was time to stop and to get real serious about finding out what was going wrong.
When they dropped a camera into the reactor core, they discovered that 13 of 43 radioactive fuel rods were damaged and partially melted. And because this was an experimental reactor, a thick concrete containment structure, such a familiar and vital part of more modern reactors, wasn't required.
It's just built in an ordinary industrial building. And in fact, it was designed so that radioactive gases would be intentionally vented from the reactor to holding tanks and then out into the environment.
Exactly how much radiation went into the atmosphere is still a matter of debate, because the monitoring equipment at the facility could only measure very minor levels of radiation. This was a much smaller reactor than the one at the site of the famous 3 Mile Island accident in Harrisburg, Pennsylvania in 1979. But because it didn't have a containment dome, the sodium reactor might have created a much bigger problem.
The SRE was about 1/100th the size of 3 Mile Island, and the containment structure at 3 Mile Island, according to the official government reports, stayed intact, and that only a small fraction of the radioactive inventory were officially estimated to get out of the 3 Mile Island reactor. And so several researchers have estimated that the radiation release from the SRE could be as high as 240 times the radiation release from 3 Mile Island.
5 weeks after the accident, the Atomic Energy Commission issued a press release claiming that just a single fuel rod had been slightly damaged and no radiation had been released.
The body of the release said there is no evidence of unsafe operating conditions. 1/3 of the fuel had experienced melting. It was one of the worst accidents in nuclear history, and the AEC essentially lied about it.
In 1961, the Atomic Energy Commission made this film, which documents the extent of the damage and cleanup process. It also explained exactly what went wrong inside this unique reactor, where molten or liquid sodium was used instead of water to remove heat from the swimming pool-sized reactor area.
Sodium reactors were being developed because there was a concern there wasn't enough uranium to fuel all of the nuclear reactors being built at the time.
Sodium reactors never deplete their original fuel supply. Water reactors are less efficient, since they consume uranium and eventually need to be resupplied. But the benefits of liquid sodium came with a price.
Sodium burns in the presence of air, explodes in the presence of water, so the reactors had tremendous danger associated with them.
Because water couldn't be near the reactor, a chemical known as tetralin was used to cool the bearings in the pumps that circulated the sodium as it carried heat away from the fuel rods. Everything worked well until tetralin started leaking through cracks in the pump seals and into the reactor.
The neutron bombardment inside the reactor core caused it to turn from an organic chemical into almost like a glue or a tar-like substance.
As the tetralin approached the fuel rods, it partially blocked the bottom of some of the coolant channels. When coolant flow decreased, the heat by those fuel rods increased and eventually reached melting point.
What happens when the fuel starts melting is the radioactive byproducts, which have been created from reactor operation, have to go somewhere. And so those radioactive byproducts go into the molten sodium, and some of those byproducts come out as a vapor, and in this case went into the air.
Some of the radioactive materials, like strontium, are actually absorbed by the body into the bones and teeth, so they remain in the body for a long period of time, all the while releasing radioactivity that can harm cells and other parts of the body.
Workers who cleaned up after the accident or worked at the facility once it was restarted were at highest risk.
The studies that were done of the workers by a team from the UCLA School of Public Health found that the workers who had the highest radiation exposures had tripled the death rates from cancers such as cancer of the lung, lymph, and blood systems, as similar workers at the site who had lower radiation exposures.
The University of California at Los Angeles was also responsible for bringing the story to the public. After the 3 Mile Island accident in 1979, some of Daniel Hirsch's students started wondering if anything like it had ever happened in Southern California. In UCLA's engineering library, they found documents and photographs of the melted fuel rods from the sodium reactor accident at the site run by Rocketdyne's Atomics International division.
And by a quirk of fate, it turned out that the man who had founded and run Atomics International had subsequently become Dean of Engineering at UCLA and taken with him box loads of the old documents. We then released that to the press in 1979. So the AEC kept it secret. And it stayed secret for 20 years.
The Atomic Energy Commission also managed to conceal accidents at 2 other reactors at the Santa Susana facility in the 1960s. Today, the reactor buildings have been torn down and taken away, but years of cleanup work remain. Health effects on the surrounding communities have been difficult to study because of their large populations and the fact that many people have moved out of or into the area over the years. And Southern California's population continues to swell. People are living closer than ever to the site, which is now owned by Boeing. And because certain types of radiation released in the accident can remain at dangerously high levels for centuries, the decisions made at Santa Susana in the 1950s and 60s will continue to affect residents for generations to come. Of the 3 most prevalent radioactive elements identified at the Santa Susana site, cesium-137 has the longest half-life at 30 years. Dangerous amounts of it will remain there for about 300 years. Engineering disasters will return on Modern Marvels. We now return to engineering disasters on Modern Marvels. 25 miles south of Pittsburgh, in the heart of one of Pennsylvania's industrial valleys, along the banks of the Monongahela River, 4 million-gallon storage tanks mark the site of a past disaster. In 1988, when the oil storage facility in Floref, Pennsylvania was owned by Ashland Oil, different tanks located in the same spots held fuel oil. On January 2nd of that year, a typically frigid winter day, a 40-year-old tank was being refilled for the first time after being disassembled in Cleveland, Ohio, and reassembled in Floref. Then, in less than 1 second, the tank cracked vertically, releasing a tidal wave of about 3.8 million gallons of oil.
When the tank split, the force of the weight of oil in the tank pushed the shell of the tank, the skin of the tank, back against this dike wall in this direction.
The oil rushed over the containment dikes in front of the split, hurtling toward other nearby tanks.
The tank that collapsed, which was behind me, released the oil. The tank that was formerly in this direction was dented by the force of the oil approximately 20 feet up on the wall of that tank. The tank was empty, but it gives you some perspective on how much force there was involved.
While some oil remained inside the dikes, the faster parts of the flow raced over the final barriers at the south end of the facility.
When the oil went off to my right, it went over the last dike in that direction into a parking lot. The parking lot has a drain in it. The oil followed that drain into the Monongahela River.
Experts estimated that between 700,000 and 800,000 gallons of oil entered the river, making this the worst oil spill in the history of this industrialized valley. The north-flowing current of the Monongahela carried the oil past a number of smaller communities, into Pittsburgh and beyond. Towns along the river were forced to shut off their water intake systems. Tens of thousands of people were without regular water service for up to 8 days. Overall, the spill temporarily contaminated drinking water supplies for about 1 million people in Pennsylvania, Ohio, and West Virginia. Contractors hired by Ashland used booms and other equipment to collect as much oil as possible from the river's surface. By the time John Gross and other investigators arrived, the oil in the dike areas had been pumped out to barges.
It was very obvious from just standing on one of the dikes, a full view of the tank, to see that it had split vertically and had begun to unpeel, like you would unpeel an orange.
When the steel split, it left behind aerolite markings, similar to the chevron stripes on a military uniform.
We found the chevron markings along this area to be pointing down, and the chevron markings along this area to be pointing up. And so just about at eye level was the confluence of those two, and this is where the fracture initiated.
At that spot was a dark area about 3/4 of an inch long. This is where it had all started.
This is a close-up of the defect in the tank wall. You can see it's this dark area here, and that dark color is caused by the carburization, which is a result of the combination of carbon and oxygen, which is present in the cutting operations that were used in either putting the tank together the first time or in reassembling.
Even today, small defects like this aren't uncommon in these huge tanks. It's hard to prevent such imperfections during large cutting and welding operations. But ordinarily, weak spots in modern tanks lead only to small leaks, which can then be easily repaired and cleaned up. Because of the speed of the collapse, the clean split, and the telltale chevron markings, investigators quickly identified brittle fracture, often a problem with weaker forms of steel dating from the 1940s and earlier, as the cause of the catastrophic failure in Fleuref. Brittle fracture has been known to plague a variety of older structures, even large ships. Tests revealed it was the main reason for the failure of this tank, which had been built in the early 1940s. And the weather compounded the problem. Sub-zero temperatures before and during the filling made the tank's old steel even more brittle. The exact location of the defect was also a factor. Welds are always weaker than the solid inner portions of a plate. When workers disassembled the tank in Cleveland, new cuts were made away from the original welds, since rewelding the same area can actually make it weaker. But when the tank was put back together in Pennsylvania, the defect happened to be in an especially dangerous spot.
The fracture occurred in this general location. This also is the location where a horizontal weld and a vertical weld come together. We call it a T-joint, and it's in this area that has particularly high stress concentrations.
Once a tank is built, welds, including T-joints, are inspected. To find defects that aren't visible on the surface, like the one in the Ashland tank, inspectors routinely use an X-ray system for metal, known as radiography.
The joints where the vertical seam and horizontal seam come together is a typical place where these radiographs are taken. That provided the opportunity to possibly identify this defect, but it was not identified.
Following the investigation of the spill, state and federal agencies put new procedures in place.
Pennsylvania implemented above-ground storage tank regulations so that tanks like this tank that failed are inspected routinely now, that they are tested routinely now in an attempt to avoid situations like this in the future. The federal government also changed its oil spill requirements in terms of equipment that needs to be available and precautions that need to be taken.
A federal grand jury indicted Ashland Oil for negligently discharging oil into the Monongahela River. The company eventually paid almost $7 million in state and federal fines. Typically, crews are able to recover only about 20% of the oil spilled on rivers. That was the approximate percentage recovered from the 1988 spill in Fleuref, Pennsylvania. Engineering disasters will return on Modern Marvels. We now return to engineering disasters on Modern Marvels. On May 19, 1998, at 6 p.m. Eastern Time, the Galaxy 4 communications satellite high above the American Midwest suddenly rotated out of position on its own. This small movement created a disastrous ripple effect below. Most of the 40 million pagers in service in the United States suddenly went silent for the first time in the 35-year history of the industry. Thousands of ATMs and credit card authorization services also failed. And several television and radio networks were unable to distribute programs to affiliates.
There were thousands of antennas on the ground, all expecting to send signals and receive signals back to the Galaxy 4. If it's pointed the wrong direction, it can't hear what the ground is trying to tell it, nor can it send signals back to the ground.
More than 80% of the nation's paging companies depended solely on the Galaxy 4. It took 3 chaotic days for technicians at Pan Am Sat, the operator of the Galaxy 4, to reroute the millions of pagers to other satellites and restore customer service. Since the satellite is still in outer space, it's impossible to inspect. But the widely accepted cause of this enormous problem is something incredibly small. A short circuit within the positioning system, created by a microscopic phenomenon known as a tin whisker. The small metal leads on microchips electronically connect the chips to other components on a circuit board, allowing for the exchange of information across the system. These leads are coated with a conductive metal to prevent corrosion. Tin is the preferred coating material because it's widely available and inexpensive. Tin whiskers are crystalline structures that grow spontaneously from this coating and can short-circuit microchip components by suddenly connecting leads that aren't supposed to be connected. Usually these leads are only 75 microns apart, meaning electron microscopes are needed to get a good look at the whiskers.
This is a picture of 2 whiskers and maybe a 3rd whisker on the side here. To give you a sense of the dimensions, these 2 whiskers are about, maybe a quarter or at least less than a half the diameter of a human hair. And the lengths are about 100 microns, and this length dimension would cross between 2 leads of this kind of a component here.
The tin whisker that caused the Galaxy 4 to fail grew from the best intentions. Researchers identified whisker growth on tin and other metals as early as the 1940s. During the 1950s, experiments revealed that adding lead to tin created an alloy that greatly reduced whisker growth. But environmental concerns about lead caused many electronics manufacturers to switch back to pure tin, beginning in the 1980s. Tin whiskers have been blamed for the complete loss of 3 satellites, and have partially damaged at least 4 others. But satellites aren't the only type of expensive and critical equipment that these tiny gremlins strike.
They've shown up in F-15 fighter aircraft radar, shown up in air-to-air missiles, heart pacemakers. In the nuclear power industry, the tin whisker problem showed up in the unplanned shutdown of the Millstone 3 plant in April 2005 in Connecticut. That problem was due to a tin whisker crossing over between circuits in a logic board.
Inside the University of Maryland's engineering department, long-term experiments are conducted over several years by subjecting closely spaced plates of tin and other metals to various temperature, humidity, and other conditions. From these experiments, researchers can determine if certain conditions inhibit or promote whisker growth. These plates are being subjected to 50% humidity at 50 degrees Celsius.
And pulling one out, if you look, basically we have a span of about 75 microns spacing between these 2 plates. If we take it over here, using this resistance measurement, if we have an open, basically we'll record nothing. If we touch these 2 surfaces, if there is a whisker, we'll see a response, and as you can see, a response is indicated, which means there is a whisker bridging these 2 surfaces.
But scientists still don't understand how to prevent these formations from occurring in the first place. Meanwhile, as electronics and microchips continue to get smaller and appear in more and more everyday products, the tin whiskers problem keeps getting bigger.
Tin whiskers are a classic example of a very small thing causing a great deal of damage. They have caused hundreds of millions of dollars in damage and are capable of causing damage in the billions.
Until science can find a solution, it seems that all industry and consumers can do is wait for the next gremlin to strike.